Hello, this is a presentation for a paper titled MetaWeather, Few-Shot Weather-Degraded Image Restoration. Today, generic image restoration models that can be used across various degradation patterns have been proposed. These models are typically trained on basic weather conditions such as rain or fog to be deployed in real-world scenarios. However, since weather conditions are continuous and not mutually exclusive, the model is likely to encounter new and untrained weather scenarios. For example, a model trained on heavy rain might be deployed in foggy rain or in a situation where both rain and fog occur together. As a result, we anticipated a decline in model performance under these conditions and demonstrated this through a simple experiment. The models shown in the figures below are all generic image restoration models, designed to be applicable to any degradation pattern. We trained these models on basic datasets, such as rain, fog, and raindrops, and then measured their performance in situations where these weather conditions occur simultaneously. As expected, the models exhibited significant performance degradation, indicating that new weather conditions can indeed lead to a decline in the performance of image restoration models. Therefore, it can be concluded that adaptation of the model is necessary to prevent such issues. On the other hand, due to the nature of image restoration tasks, pixel-by-pixel labeling is required, which is highly costly. Therefore, data efficiency must be prioritized. Based on these two problems, we propose a few-shot domain adaptation method for weather-degraded image restoration in this study. Before developing the method, we first analyzed the characteristics of the data, as shown in the image below. We found that images captured under the same weather conditions share similar weather degradation patterns and have many overlapping features. We also observed that the distribution of degradation patterns is less diverse compared to the distribution of backgrounds. Therefore, based on the findings, we were motivated to develop a method that focuses on and generalizes to these degradation patterns. Our method is divided into two main components. One is the architecture, and the other is the training approach. This diagram illustrates the architecture of our method. The architecture consists of an encoder, matching modules, and a decoder. First, the encoder processes the query image and the support set. In the matching module, the degradation pattern of the query image is interpolated from the degradation patterns extracted from the support set. Finally, the decoder constructs the degradation pattern of the query image generated by the matching modules. By subtracting the constructed degradation pattern from the degraded query image, the restored query image is generated. As a result, our model focuses on degradation pattern of the data. To describe the matching module in more detail, the query consists of the features of the query image, while the key consists of the features of the support image. Therefore, the computed attention map represents the similarity between the degraded features of the two images, and since the value is the degradation pattern of the support image, the resulting output is the degradation pattern of the query image. The matching module is divided into spatial matching and channel matching. Spatial matching handles particles such as rain streaks and weather effects, while channel matching addresses atmospheric effects like fog. Next, regarding the training strategy, it is divided into two stages, meta-training and meta-testing. In the meta-training stage, a batch is divided into query and support sets to mimic meta-testing for training. During this stage, all parameters are trained to learn a generalizable representation. In the meta-testing stage, only the bias parameters are trained, which helps preserve the generalizable representation learned during meta-training and prevents overfitting. Next is the experimental section. In the meta-training stage, an independent weather dataset is used for training, while in the meta-testing stage, training is performed with combinations of various weather conditions. The dataset used in meta-training consists of rain, snow, fog, and raindrop. In meta-testing, adaptation is performed under conditions where multiple weather phenomena co-occur, and inference is carried out under these conditions. Additionally, to account for the domain gap with real-world data, we used real-world data in the meta-testing phase for experimentation. The table below shows the results for co-occurring weather types. Our model achieved the highest average PSNR and SSIM. The table below shows the results with real-world data. Our model achieved the highest performance in all cases. Starting from this slide, I will explain the ablation study. This study compares performance based on whether the matching module focuses on matching background features or degradation patterns. As shown below, concentrating on degradation patterns consistently results in higher performance across all cases. This confirms that our design consideration was effective. This table shows the ablation study of spatial and channel matching in the matching module. It confirms that performing matching in both spatial and channel directions achieves higher performance. This slide demonstrates that our model achieves the highest performance regardless of the number of support sets. Next, to demonstrate the robustness of support set selection, we conducted experiments by repeatedly changing the support set. The results show that the standard deviation is very small, confirming that the model is robust to variations in the support set. Thank you for listening.